The Sherman tank sits motionless in the Libyan desert, like a steel tomb baking under African sun that transforms armor plating into griddles, capable of cooking eggs on contact, radiating heat that makes crew compartments uninhabitable within hours of dawn, creating thermal conditions that exceed every assumption American engineers made about operational temperatures. When designing tanks in Detroit factories where summer heat rarely exceeds 90 degrees and humidity provides cooling that desert air cannot deliver through moisture evaporation that simply doesn't exist in landscapes, where water is more precious than gasoline and mechanical cooling becomes matter of life or death for crews whose survival depends on keeping engines running despite environmental conditions that challenge every principle of automotive thermal management developed through peacetime engineering that emphasized mass production, efficiency over specialized performance requirements. Sergeant Mike O'Brien crawls beneath the disabled Sherman with welding equipment that shouldn't exist in forward positions, tools he acquired through unofficial channels that supply mechanics with materials needed for field modifications that Army regulations prohibit. But battlefield necessity demands when standard repair procedures prove inadequate for combat, conditions that equipment manufacturers never anticipated. During peacetime development programs, emphasizing cost reduction over performance optimization, creating equipment that functions adequately under temperate conditions but fails catastrophically when environmental factors exceed design parameters that Detroit engineers established through testing conducted in climate-controlled facilities rather than actual operational environments where equipment must function reliably despite conditions that challenge every assumption about acceptable operational parameters. Around him, the scattered remains of an entire armored company bear silent testimony to thermal failure that eliminates more Allied tanks than German anti-tank guns. Engines seize through overheating that conventional cooling systems cannot prevent despite adequate coolant levels and properly functioning radiators. Transmissions destroyed by lubricants that become useless under temperatures that exceed viscosity specifications established through laboratory testing rather than field evaluation. Electrical systems failed through heat-induced component breakdown that renders sophisticated military equipment as worthless as scrap metal in landscapes where survival requires mechanical reliability that American industrial engineering has not achieved through manufacturing processes optimized for quantity production rather than extreme environment operation under conditions that challenge fundamental assumptions about equipment durability. The copper tubing he shapes into impossible spirals represents engineering heresy that violates established principles of cooling system design taught in automotive engineering programs, creating flow patterns that thermodynamics textbooks suggest would reduce rather than enhance heat transfer efficiency through increased pressure drops and turbulent flow that conventional analysis considers counterproductive. Yet his understanding of fluid mechanics gained through years of automotive repair under conditions that formal engineering education never addresses enables innovations that academic theory cannot explain through conventional analysis but practical experience. Validates through results that exceed theoretical predictions when creative problem-solving meets desperate necessity under operational pressure. This is July 1942. The North African campaign has revealed catastrophic inadequacies in Allied tank design that threaten entire strategic operations planned by military leaders who assumed American industrial superiority would translate directly into battlefield effectiveness, where tanks superior in firepower and armor protection become useless through mechanical failure caused by environmental conditions that German equipment handles successfully through engineering, adapted for extreme temperatures during development programs that incorporated lessons learned from earlier campaigns in similar climates, where tactical advantages disappear when American armor cannot operate for extended periods without catastrophic overheating that eliminates combat effectiveness more efficiently than enemy action. The desert warfare environment creates thermal challenges that peacetime engineering never anticipated through testing programs conducted in temperate climates, where ambient temperatures exceed 130 degrees Fahrenheit, while direct solar radiation adds another 40 degrees to exposed metal surfaces, creating surface temperatures that approach engine operating levels, where cooling air provides no relief through temperatures that eliminate thermal differential necessary for conventional radiator operation, where traditional automotive cooling depends on environmental heat dissipation that desert conditions prevent through atmospheric temperatures that make conventional cooling systems inadequate for sustained operation, under combat stress requiring continuous mechanical operation. British tank crews operating American Lend-Lease equipment report operational endurance measured in hours rather than days, with vehicles becoming uninhabitable through internal temperatures that cause heat exhaustion before noon, mechanical systems failing through thermal stress that exceeds design limits established through laboratory testing under controlled conditions. Mission effectiveness compromised through equipment that cannot maintain operational status during daylight hours when tactical requirements demand sustained combat capability regardless of environmental conditions that challenge human and mechanical endurance beyond peacetime operational parameters that equipment manufacturers never considered during development, programs emphasizing cost efficiency over extreme performance capability. German tank crews operating equipment specifically designed for extreme climate conditions demonstrate superior operational endurance through cooling systems developed for tropical and desert operations. Mechanical reliability that enables sustained combat effectiveness despite environmental conditions that disable Allied equipment. Tactical advantages gained through equipment that functions reliably under conditions where American tanks become liabilities rather than assets, proving that engineering adapted for specific operational environments provides decisive military advantages over equipment designed for general-purpose applications that prove inadequate when specialized performance becomes essential. For combat effectiveness, O'Brien's mechanical background includes Depression-era automotive repair experience that developed understanding of cooling system modifications for vehicles operating under extreme conditions, including agricultural equipment used in southwestern states, knowledge of heat transfer principles gained through practical application rather than theoretical study during formal engineering education, innovative problem-solving techniques that adapt standard components for specialized applications requiring performance beyond manufacturer specifications, creating foundation for field modifications that violate engineering orthodoxy while serving essential operational requirements that conventional equipment cannot meet through standard design and manufacturing approaches. His unauthorized experiments with cooling system modifications begin through desperation rather than scientific curiosity, observing thermal failure patterns that suggest inadequate heat dissipation capacity rather than excessive heat generation by properly functioning engines. Recognizing that cooling system efficiency rather than engine output represents limiting factor for desert operations where environmental conditions overwhelm conventional thermal management capabilities. Understanding that enhancing heat transfer through innovative design could extend operational endurance even under environmental conditions that challenge equipment design. Assumptions and manufacturing specifications established for temperate climate operation. The spiral tubing concept emerges through observation of natural heat transfer phenomena that suggests increased surface area could enhance cooling efficiency despite reduced flow rates that conventional engineering considers counterproductive. That turbulent flow created by curved passages might improve heat exchange through enhanced mixing despite creating pressure drops that standard radiator design avoids. The creative geometry could achieve thermal performance, improvements that conventional straight tube construction cannot accomplish through parallel flow patterns that optimize manufacturing efficiency rather than heat transfer capability under extreme operational conditions. The theoretical basis for spiral cooling enhancement involves increasing heat transfer surface area through geometric configuration that provides more contact between coolant and heat exchanger surfaces, creating turbulent flow patterns that enhance convective heat transfer through improved mixing between hot and cool fluid layers. Optimizing residence time that allows maximum heat exchange before coolant returns to engine block, demonstrating that innovative geometry can achieve thermal performance improvements that conventional design approaches had not exploited through conservative engineering that prioritizes manufacturing simplicity over performance optimization under specialized operational requirements. The implementation requires welding skills that most tank mechanics possess through maintenance training programs that emphasize field repair capabilities, metalworking techniques that equipment maintenance develops through necessity when replacement parts are unavailable in forward positions, understanding of cooling system hydraulics that automotive experience provides through practical application during civilian employment before military service, demonstrating that innovative modifications utilize knowledge base that military mechanics already possess rather than specialized engineering education that formal institutions would require for similar technological development and practical application under field conditions. The fabrication process involves forming copper tubing into spiral configurations that maximize surface area within existing radiator housing dimensions, creating flow patterns that enhance heat transfer through turbulent mixing while maintaining adequate flow rates for engine cooling requirements. Installing modified heat exchangers without compromising other cooling system components or vehicle operational capability, demonstrating that field modifications can achieve significant performance improvements through creative application of readily available materials and standard mechanical skills that military training provides. The initial testing reveals cooling performance improvements that exceed theoretical predictions for modified heat exchanger design based on conventional engineering analysis, achieving operational endurance that doubles standard Sherman tank capability under identical environmental conditions that disable unmodified vehicles within hours, demonstrating practical results that contradict academic understanding of optimal cooling system configuration while proving that field innovation can achieve performance breakthroughs that formal engineering development had not accomplished through systematic research and controlled laboratory testing under simulated rather than actual operational conditions. His modified Sherman operates for 12 continuous hours under desert conditions that disable unmodified tanks within 6 hours of sunrise, maintaining engine temperatures within acceptable ranges, despite ambient heat that exceeds cooling system design parameters established during temperate climate testing, proving that spiral tubing configuration enhances heat transfer through mechanisms that conventional engineering analysis had not identified or exploited through standard radiator design and manufacturing processes optimized for mass production, rather than extreme performance applications requiring specialized thermal management capabilities. The performance demonstration attracts attention from tank commanders whose units face operational limitations through thermal failures that compromise mission effectiveness and tactical flexibility, whose combat capability depends on mechanical reliability that standard equipment cannot provide under desert conditions where environmental factors eliminate equipment advantages, whose tactical planning must account for thermal constraints that limit operational options and reduce strategic effectiveness through equipment limitations that innovative field modifications might address through creative engineering solutions that challenge conventional design assumptions. Captain Robert Hayes, the battalion maintenance officer responsible for evaluating field modifications that could enhance operational capability without compromising equipment reliability or safety standards, observes O'Brien's cooling system performance with professional interest that balances skepticism about unauthorized modifications against recognition of demonstrated improvements that exceed standard equipment capability under realistic operational conditions, understanding that thermal management represents critical limitation for desert tank warfare, that innovative solutions might address more effectively than conventional approaches. His evaluation includes comprehensive performance testing under controlled conditions that measure cooling efficiency improvements, operational endurance extensions, system reliability under stress conditions, demonstrating that spiral tubing modification provides consistent improvement over standard cooling systems while maintaining mechanical reliability that combat operations require for sustained effectiveness, proving that field innovation has achieved thermal management breakthrough that formal engineering development had not, accomplished through conventional research methodology and established design principles that limit creative problem solving. The technical analysis reveals heat transfer enhancement through increased surface area that spiral configuration provides within existing radiator housing constraints, improved turbulent mixing that enhances convective cooling through better fluid dynamics, optimized flow patterns that maximize heat exchange efficiency despite reduced flow rates that conventional engineering considers problematic, demonstrating that innovative geometry achieves thermal performance improvements through mechanisms that engineering education emphasizes theoretically but rarely exploits, practically through creative design applications that challenge conventional assumptions. The broader testing program includes multiple tank modifications using standardized spiral tubing configurations developed through systematic analysis of O'Brien's prototype design, comparative performance evaluation under various environmental conditions that simulate different operational scenarios, reliability assessment through extended operational periods that test system durability under combat stress, demonstrating that cooling system innovation provides consistent improvement across different vehicle types and operational scenarios while maintaining mechanical simplicity that field maintenance can support without specialized technical training. The scientific investigation involves collaboration with engineering specialists who analyze thermal performance improvements through mathematical modeling that explains spiral tubing effectiveness, fluid dynamics research that validates turbulent flow benefits, heat transfer calculations that confirm surface area advantages, providing theoretical foundation for practical innovation that supports systematic implementation across tank units while addressing institutional skepticism about field modifications that challenge established engineering principles and manufacturing standards. The adoption decision requires balancing demonstrated effectiveness against implementation challenges, including modification procedures that ensure consistent results, training requirements that enable mechanics to perform installations properly, supply chain development for specialized components not included in standard military procurement, regulatory approval for alterations to standard military equipment that involves safety and reliability considerations, overcoming institutional resistance to field modifications that challenge established engineering assumptions. The systematic implementation includes establishment of modification procedures that standardize spiral tubing installation across tank units through detailed technical instructions, development of comprehensive training programs that teach mechanics proper installation techniques and maintenance procedures, creation of supply networks that provide copper tubing and welding materials necessary for cooling system modifications, ensuring quality control that maintains performance improvements while preserving mechanical reliability essential for combat operations under demanding conditions. The training curriculum covers fundamental heat transfer principles that explain how spiral configuration enhances cooling efficiency through increased surface area and improved flow dynamics, detailed installation procedures that ensure proper modification without compromising system integrity or vehicle reliability, maintenance techniques that preserve performance improvements under combat conditions where equipment stress exceeds peacetime operational parameters, troubleshooting methods that enable field repair of modified cooling systems without specialized technical support or replacement components unavailable in forward positions. The supply network development includes procurement of specialized copper tubing that meets military specifications for durability and performance under extreme conditions, distribution systems that deliver modification materials to forward positions where tank units operate, Quality control procedures that ensure component reliability through inspection and testing protocols. Inventory management that maintains adequate supplies for ongoing modification. Programs and maintenance requirements that extended operations under extreme conditions impose on cooling system components, requiring periodic replacement. The strategic implications extend beyond immediate thermal management improvement to encompass enhanced operational capability through extended mission endurance that enables longer combat operations, improved tactical flexibility through reduced thermal constraints that limit operational planning, demonstration that field innovation can solve engineering problems that formal development programs had not addressed through conventional research methodology and established design assumptions that limit creative problem-solving under operational pressure requiring immediate solutions. The operational advantages include extended combat endurance that enables longer missions without thermal failure that forces tactical withdrawal, improved crew survivability through reduced internal temperatures that prevent heat exhaustion, enhanced mechanical reliability through optimized cooling that prevents heat-related component failure, maintained combat effectiveness during daylight hours when environmental conditions would otherwise force equipment shutdown that compromises mission objectives, and strategic effectiveness in desert warfare where thermal management determines operational capability. The tactical benefits include improved battlefield flexibility through tanks that remain operational during peak heat periods when unmodified equipment becomes unusable, enhanced mission planning options through extended operational endurance that enables longer-range operations, reduced logistical requirements through decreased cooling system maintenance and component replacement, improved crew morale through equipment that functions reliably under conditions that previously caused mission failures, and equipment casualties. Post-war analysis credits O'Brien's cooling modification with enabling desert tank operations that standard equipment could not sustain through thermal limitations, demonstrating value of field innovation that challenges engineering orthodoxy through practical solutions to operational problems that formal research had not solved, proving that mechanical creativity can achieve performance, breakthroughs that systematic development had not, accomplished through conventional methodology designed to optimize mass production rather than specialized performance under extreme conditions. The spiral tubing principles become foundation for modern cooling system design that recognizes geometry optimization as essential thermal management tool requiring creative application of heat transfer principles that incorporates field-derived innovations with theoretical understanding to develop improved systems, that demonstrates how practical necessity can drive engineering advancement beyond conventional limitations when creative problem-solving meets operational requirements that standard solutions cannot address through established methodology designed for normal, rather than extreme operational conditions. O'Brien continues military service with understanding that field innovation serves essential operational needs when standard equipment proves inadequate under conditions that exceed design parameters, that practical mechanical knowledge can contribute to engineering advancement through creative solutions that formal education might not identify through theoretical analysis alone, that individual innovation can influence military capability when institutional flexibility supports proven improvements regardless of their unconventional development, through field necessity rather than systematic research. His technical legacy influences thermal engineering development that recognizes heat transfer enhancement through geometric innovation as viable approach to cooling system optimization, that incorporates practical field experience with theoretical research to develop improved designs, that demonstrates how individual creativity can contribute to systematic capability improvement when military institutions maintain flexibility toward modifications, that enhance operational effectiveness despite challenging established engineering assumptions and manufacturing standards. The cooling modification that seemed mechanically impossible becomes symbol of field innovation solving engineering problems that formal development could not address, Practical wisdom overcoming theoretical limitation through creative application of available materials. Individual creativity contributing to military effectiveness through solutions that systematic research had not achieved despite extensive resources and formal methodology, proving that desperate necessity often drives breakthrough innovation beyond conventional engineering boundaries. Years later, when thermal engineering specialists analyze factors contributing to cooling system advancement, they cite field innovations that challenged established design principles as essential developments that enhanced equipment capability despite unconventional origins, demonstrating that breakthrough solutions often emerge through practical necessity rather than systematic research, proving that institutional flexibility toward innovation can yield strategic advantages when proven improvements are adopted regardless of their development through field experimentation. If stories like this remind you that practical innovation often exceeds theoretical limitation when necessity drives creative problem-solving, that field experience can reveal solutions that formal engineering overlooks through conventional analysis. Then perhaps there are other moments of mechanical creativity solving impossible problems worth remembering, worth celebrating, worth carrying forward into whatever challenges require us to question engineering orthodoxy and embrace creative solutions that serve essential needs despite violating established assumptions.